Hi, I'm Lars Heppensteel at the Gatton Academy of Math and Science at Western Kentucky University, and in this talk, we will be talking about my numerical and experimental study of stochastic resonance in bistable systems. First, we will discuss stochastic resonance, its definition and origin, and how it shows up in bistable systems. Next, we will talk about the Duffing oscillator, its mathematical description, and some physical models. We will combine those two ideas and then talk about stochastic resonance in the Duffing oscillator, and then we will look at our numerical study and its results. Finally, we will look at our future work for this research. Section 1, Stochastic Resonance. Stochastic resonance is defined to be a phenomenon which occurs when the optimal amount of noise is added to a system such that the signal-to-noise ratio is maximized. This is a quite obtuse definition, however. So what does this actually mean? The simpler definition for stochastic resonance is that it's a phenomenon which occurs when an output signal is enhanced or boosted by systematically adding noise to the input. Stochastic resonance originated as an explanation for periodic ice age recurrence in 1989 in a paper published by Roberto Benzi. Since then, stochastic resonance has been introduced into many fields such as engineering, physics, chemistry, and even sociology. In general, stochastic resonance can be applied to almost any system with two stable equilibria. In figure 2, we see a potential function with two equilibria at xm and negative xm because those are the lowest points of the potential function. So why do we add noise? The concept of adding noise is quite counterintuitive at first, because why would we add noise to enhance something or to boost something? Well, in figure A, we see a signal which is below threshold, so we don't get an output from the signal at all. When we add noise, the signal has a chance to randomly jump above the threshold and produce an output. When we add slightly too much noise, the signal still gives a reasonable output, but it's less good than the optimal amount of noise. And when we add too much noise, our output gets completely swamped with false positives from the signal jumping above the threshold because the noise is too strong. So how do we determine whether or not stochastic resonance is occurring? In mathematics, there's a function called the Fourier transform, which lets us see how much a frequency shows up in the output. In figure A, the blue function is our output and the orange function is our periodic input function with frequency 0.01. In the Fourier transform there, at 0.01, we see an amplitude of about 0.05. In figure B, we can see our blue function is much more closely following the orange function, and this is reflected in the Fourier transform as well. At 0.01, we have an amplitude of about 0.4. In figure C, when we add too much noise, we still get an amplitude of about 0.23 at frequency 0.01, but in general, our output is much more noisy and less useful. So if we combine this idea and plot the amplitude of the Fourier transform at 0.01 as a function of how much noise is added, we see this stochastic resonance curve, as it's called. Section 2, the Duffing oscillator. To derive the differential equation of the Duffing oscillator, we first consider a potential function of the form a over 4x to the fourth minus b over 2x squared. Taking the negative derivative of this with respect to position, we get the forcing function bx minus ax cubed. Using Newton's second law and adding both a damping and driving force, we get the differential equation of the oscillator. Here, delta is the damping coefficient, and f cosine omega t is our periodic driving force. Here are two mechanical models of the Duffing oscillator. In figure A, the small solenoid and the large solenoid acting on the magnet, combined with the spring acting on the magnet, reconstructs the Duffing potential. In figure B, instead of having two solenoids, there are two electromagnets acting on two permanent magnets which are attached to a beam. The beam and the magnets both work together to reconstruct the Duffing potential here as well. We can also build an electrical circuit to act like the Duffing oscillator. We're currently constructing this circuit and a data acquisition system using LabVIEW as a class project for Physics 318. Section 3, Stochastic Resonance in the Duffing oscillator. What does stochastic resonance look like in the Duffing oscillator? Specifically, where's the noise? Well, we need to modify the differential equation to add a noise term, nu of t, which is a Gaussian white noise with a standard deviation sigma nu. Where's the signal and where's the output? Well, our signal here is our periodic forcing function f cosine omega t, and our output is the position over time of the oscillator. The transition rate between the wells of the oscillator is given by the Kramer's rate Rk, where d is the noise intensity. Taking the waiting time tk to be half the period t omega, we get the timescale matching condition, which we can solve for the optimal noise value. Section 4, numerical study. The Duffing equation with noise is a part of a special class of differential equations called stochastic differential equations. And because of this, using regular numerical methods like Runge-Kutta, which are used to solve ordinary differential equations, does not work. Instead, we elect to use the stochastic Runge-Kutta algorithm, SRS2, proposed by Andreas Rösler in the Siam Journal on Numerical Analysis. Although it has Runge-Kutta in the name, this method is only loosely related to Runge-Kutta. The way it's constructed allows for additive noise to be added to a differential equation. For all the calculations we're about to show in this presentation, we used the following SDE. The parameter f is intentionally left undefined because varying it can produce both chaotic and stable behaviors. Phase portraits plot the velocity and position together to visualize the exchange of energy. So in figure A, stable behavior is shown. And so the correct way to interpret this is, even though the oscillator changes its position and changes its velocity over time, it'll always be on that orbit. For a chaotic behavior, the oscillator instead has these loops and swirls around the two equilibria at -1, 1 on the position and 0 on the velocity. Poincare maps build on the idea of phase portraits by sampling the position of the oscillator, the location of the oscillator on the phase portrait every time the forcing function completes a cycle. So for a stable behavior, this means there's only one point, because every time the forcing function completes a cycle, the oscillator has returned to the same point on the phase portrait. And so in this example, that would be around 0.4 on the position and 0.2 on the velocity. For a chaotic behavior, we instead get this fractal-looking Poincare map, where we aren't entirely sure where the oscillator will show up next time the forcing function completes a cycle. And so this is why this type of behavior is called chaotic. Bifurcation diagrams are another way to visualize chaos and stability in the oscillator. Instead of plotting both position and velocity, they only plot position, but they also change a parameter on the differential equation. So in this example, we changed the forcing strength of the oscillator and then plotted the position of the oscillator every time the forcing function completed a cycle. At forcing strength 0.3, the oscillator will be at one of 2 points, either at 0.4 or -1.3. When we increase the forcing strength to about 0.31, or shortly before, it undergoes a pitchfork bifurcation, and now there are 4 possible locations the oscillator could be located at. Increasing the forcing strength all the way past around 0.341, the oscillator goes into a chaotic behavior where we don't know where the oscillator will be after the forcing function completes another cycle. As we mentioned earlier, the stochastic resonance curve characterizes how much the input signal affects the output signal. The stochastic resonance curve for this oscillator is rather interesting. The reason for the spike at 0 noise is because the natural frequency of the oscillator is the same as the forcing frequency of this oscillator. So when 0 noise is added, the Fourier transform actually picks up the natural oscillation. When we then add noise up until around 0.2, this natural oscillation is destroyed. But then after 0.2, stochastic resonance starts to take effect, and the oscillation starts to come back. This happens until about 0.5, after which it starts to diminish again. Section 5, future work. Over the summer of 2020, we will be building this mechanical model we showed earlier in the presentation. This project is supported by the Kentucky Academy of Science undergraduate summer research grant. For the data acquisition and analyzing, we will use the same program in LabVIEW as we did for the electrical model built in our Physics 318 course this semester. We've also applied for a FUSE grant from WKU for the fall 2020 semester to improve the sensitivity of a gas chromatography column using stochastic resonance. In Figure A, the gas chromatography column sensor is shown. This setup is available at the Applied Physics Institute in Bowling Green. On Figure B, our proposed mechanism for enhancement is shown, with the bistable system highlighted. I would like to thank these people for help with my research, and especially I would like to thank Dr. Ivan Novikov for being my research mentor. Thank you for listening.